And today's my talk is based on joint work with Stefan. So it's welding of backward SLE and tip of forward SLE. So this is 4 sections. First section, we call the forward coordinate equation is this. Z is any complex number. Lambda is a driving function, is a continuous function. If lambda t equals square root of kappa times Brownian motion, kappa is a positive number, then the solution is called coordinate SLE kappa. Okay, this is well known. Rode and Schramm show that coordinate SLE kappa generates a random curve called the trees in the closed upper half plane, which start from 0 and go all the way to infinity. We are focused on the simplest case, where kappa is less than or equal to 4, in which gamma is a simple curve with when t greater than 0, it stays in the open upper half plane, and gt maps h without gamma from 0 to t conformally onto the upper half plane. Such gamma, we call it as an H-simple curve. By H-simple curve, we mean a half-open simple curve in the upper half plane whose open end approaches a point on the real line. Adding a minus sign to the forward coordinate equation, we get the backward coordinate equation. This is backward coordinate equation. Setting lambda t equal to square kappa times Brownian motion, we then get the backward coordinate SLE kappa. Suppose kappa is less than or equal to 4. The backward coordinate SLE kappa generates a family of H simple. Thank you. Thank you very much. Such that for every t, ft is a conform map from H onto H without beta t. The backward coordinate SLE kappa does not naturally generate a single curve because beta t is not an increasing family. We will instead study a different object, which is the conformal welding. For technical reasons, we introduce a 2-parameter family of conform maps, ft to t1, which are solutions of following equation. You can think of it as the backward SLE driven by lambda from interval from t1 to t2. So it satisfies those equations. ft2 t1 compose ft1 t0 equal to ft2 t0. Okay. Every ft has a continuous extension from the open half plane to the closed upper half plane, which maps to real intervals with common endpoint 0 onto the 2 sides of beta t. And if ft of x1 equal to ft of x2 on the beta t, then we write x1 is equivalent to x2 at the time t. Now if t1 less than t2, then from that equality we see that x1 is equivalent to x2 at the time t1, implies that x1 is equivalent to x2 at the time t2. Thus we may define a global relation x1 is equivalent to x2 if there exists some t so that x1 is equivalent to x2 at time t. In fact, x1 is equivalent to x2 if and only if the solution ft of x1 and ft of x2 blow up at the same time. Okay. It holds that almost surely the tau of x is less than infinity for every x. So every point will blow up at some finite time. So we get a random evolution phi, which is homeomorphism whose inverse is itself of the real line, so that 0 is fixed and positive infinity and negative infinity are swept. And y equal to phi x implies x is equivalent to y. We call such phi a backward coordinate SLE kappa welding. An important property of the forward coordinate SLE is reversibility. As for kappa less than or equal to 8, the law of the SLE kappa trees is invariant under the automorphism z mapped to -1 over z of h modulo time parameterization. Okay. Our main theorem is that the backward coordinate SLE kappa welding has the following symmetry. That's if kappa is less than or equal to 4, and phi is a backward coordinate SLE kappa welding, and if h of z equal to -1 over z, then the composition h compose phi compose h has the same distribution as phi. Phi is random involution. Shear field proved that for kappa less than 4, there is a coupling of a backward quarter SU kappa with a free boundary Gaussian free field in the upper half plane, such that for x less than 0, less than y, phi of x equal to y, if and only for the interval x0 and interval 0y have the same quantum length determined by the Gaussian free field, usual quantum length. It's not obvious to us how our main theorem follows from shear field results. Instead, the proof of our theorem uses an idea in the proof of the reversibility of fold called SU kappa for kappa less than equal to 4. So I don't know whether somebody knows how can use shear fields work to prove our results. Now we'll explain the conformal transformation. First, we fix some notation. A relatively close subset K of H is called an H hat if K is bounded and H without K is simply connected. Now assume K is an H hat and let I of Z be the reflection about the real line. The base of K is defined to be the intersection of the closure of K with the real line. The double of K is the K union is the reflection union the base. The GK is a unique conformal map from the H without K onto H so that it satisfies that normalization. The GK then extends to a conformal map, still called GK, defined on the compact plane without the double of K. The support of K is the subset of R, so that C without SK is the GK image of the C without K double. The H capacity of K is defined by that formula, which is non-negative. The FK is the inverse map of GK, which is defined on the complement of the support. Now, every H simple curve is an H hat. It's an easy example, whose base is its root and whose support is a real interval. An H simple curve beta induces a Welding phi beta, which is an involution of S beta swapping its two endpoints, such that y equal to phi beta of x implies that f beta of x equal to f beta of y. Note that f beta maps the two endpoints of S beta to the base of beta, and maps the only fixed point of phi beta to the tip of beta. Now let kappa be less than or equal to 4 and beta t be the H simple curves generated by a backward SL kappa process. Then ft equal to f beta t for every t. The beta t is the map associated with beta t. And the union of S beta t is the real line. The SL kappa welding phi satisfies that phi is restricted to the support of beta t equal to phi beta t for every t. Also, we introduce the quotient hat. If K and L are two H hats and L is subset of K, then we define another H hat by this map. It's the GL image of K without L. Call it a quotient hat of K. And we use that symbol to denote the quotient hats. A simple fact is if M is a quotient hat of K, then the H capacity of M is less than or equal to H capacity of K, and the support of M is subset of support of K. Here's a proposition. It's not difficult. Let beta t be a family of H simple curves. Then they are generated by a backward coordinate equation if and only if T1 less than T2 implies that beta T1 is a quotient hat of beta T2, and 2 is normalized so that the half plane capacity of beta t equal to 2t. If part the one holds, then the family beta t induces a welding of the union of S beta t as follows. First, if T2 is greater than T1, then phi beta T2 extends phi beta T1. So the phi is then defined on the union of support such that the phi is restricted to the support of beta T equal to phi beta T for each T. Now we have a theorem which is not trivial. Let W be a conformal map with a domain omega. Suppose omega and W are symmetric in the sense that omega is symmetric about the real line, and W commutes with the reflection about real line. Let K be an H hat so that the support of K is contained in omega. Then there is a unique symmetric conformal map for WK. defined on omega k. Omega k is defined to be the fk image of omega without support of k, then union the k double. So that wk compose fk equal to f sub wk of k compose w. And moreover, the support of wk of k equal to w image of sk. And if k1 is a quotient of k2, and the support of k2 is containing omega, then wk1 of k1 is a quotient of wk2 of k2. We use wh of k to denote the image wk of k, which is also an h Hall. Okay, I'll use a picture to explain this theorem. At the beginning, we have the omega sk and the w. We also have k. Now, so since we know the k, so we also have the fk image. So we have three graphs, three pictures. Now the top right picture is unknown. So the theorem says that you can find a conform map wk defined on the omega k, which contains the k double, which makes the diagram commute. So if you choose randomly any conform map, symmetric conform map wk defined on that omega k, then you can have wk of k. Then it automatically determines this error, but then the diagram may not commute. That's a unique map which makes this commute. And if you start with wk, so start with the top two configuration, then you automatically can find the w. So go from wk to w is easy, but go from w to wk is not trivial. Okay, I'll explain why this is useful. The proof of this theorem uses results on conformal welding. The idea is to first consider the case that k is an analytical H-symbol curve, and then extend the result to the general case using approximation. Now we explain why the theorem is useful. If k equal to beta is an H-symbol curve, then so is WH of beta. Now beta and WH beta induce welding phi beta and phi WH of beta, which are involutions of support beta and support of WH of beta. And support of WH of beta equal to the W image of the support of beta, respectively. From that commutation, we get the following relation. The phi WH of beta equal to W compose phi beta compose W inverse. Suppose W beta t are generated by a backward known equation, so that the support of beta t is contained in omega for every t. If t1 less than t2, then beta t1 is a quotient of beta t2. So WH of beta t1 is a quotient of WH of beta t2. But now WH of beta t may not be normalized by that relation. This can be handled by a time change. We are familiar with this. Let ut equal to the half plane capacity of this divided by 2. Then u is continuous increasing and starts from 0. And now we consider WH beta u inverse of t. Then it's normalized, and so are generated by a backward known equation. We call this family the conformal transformation of beta t via w. So this is the conformal transformation. Let phi and phi w be the welding induced by beta t and the conformal transformation, respectively. Then there are involutions of S and SW equal to union of SWH of beta t, respectively. And we have the SW equal to W of S, the W image of S, and phi W equal to W compose phi compose W inverse. Now we define backward caudal SLE kappa 0 process. The 0 is a real number. We fix two distinct real numbers. Suppose lambda t and pt solve the following equations. Okay, it's very similar to the forward SLE kappa 0. Then we call the backward caudal known process driven by lambda the backward caudal SLE kappa 0 process starting from x, y. Those are marked points. I want to emphasize that this definition differs by a minus sign from definition in Sheffield's paper on quantum gravity zeta. our backward SL kappa 0 is called backward SL kappa negative 0 in Sheffield's paper. Here's the theorem, which is not difficult. Let W be a converged automorphism of H so that W0 is not infinity. And let kappa be less than equal to 4, and beta T be backward called SL kappa traces. Suppose that we assume W inverse of infinity is not contained in the supports. Then the conformal transformation of I did not say it was T. I guess it's infinity. T should be infinity. Then the conformal transformation of not infinity. It's the first time that W inverse of infinity is contained in the support. Then the conformal transformation of beta T up to T, capital T via W is a backward called SL kappa negative kappa minus 6 process. This theorem is similar to work by Schumann and Wilson, who showed that the image of a forward called SL kappa process under a conformal automorphism of upper half plane is an SLE kappa minus 6 process. So the resemblance makes us to believe that the backward SLE kappa can be understood as SLE with negative parameter negative kappa. We may similarly develop the theory of backward radial SLE, where the unit disk plays 0 of the upper half plane, the center 0 plays 0 of infinity, and the circle plays 0 of unit circle plays 0 of real 9. So the backward radial normal equation differs from forward equation by a minus sign. If the drawing function is square kappa bound motion, we get backward radial SL kappa. If kappa is less than equal to 4, a backward radial SL kappa process generates a family of D simple curves and a conformal welding, which is a random involution of the unit disk with 2 fixed points. We may define D halls, the base and the support of a D hall, which are subset of the unit circle, and the quotient halls of D halls. It turns out that the D symbol curves beta T generated by a backward radial SL kappa process satisfy that if T1 is less than T2, then beta T1 is a quotient hall of beta T2. We may also define the transformation of a backward radial normal process via a conformal map and get another backward radial normal process. And we may define the backward radial SL kappa 0 process starting from AB, where AB are distinct points on the unit circle. Now I'll talk about the conformal commutation coupling. Now, if W is a conformal map from the upper half plane onto the unit disk, then we may similarly define the conformal transformation of a backward caudal normal process via W and get a backward radial normal process. The theorem below also resembles Schumann-Wilson's result. The theorem says that suppose W maps the upper half plane conformally onto the unit disk and kappa is less than equal to 4. Beta T are backward caudal SLE traces. Then the conformal transformation of beta T via W is a backward radial SLE kappa minus 6 process started from W0, W infinity. A backward SLE kappa minus 6 process starting from W0, W infinity induces a welding phi W, which is an involution of the unit disk with 2 fixed points. One is W0, the other is W infinity. If phi is welding induced by the backward caudal SLE kappa traces beta T, then phi W equal to W compose W inverse. Now fix T1, fix 2 distinct points on the unit disk. To prove the main theorem, it suffices to show that we may couple a backward radial SLE kappa minus 6 process starting from Z1, Z2 with another backward radial SLE kappa minus 6 process starting from Z2, Z1, such that the 2 processes induce the same welding. Now the theorem, we got the following theorem. So we say there exists a coupling of 2 families of these simple curves, beta 1t and beta 2t, so that the following hold. Suppose J is 1, K equal to 2, or J equal to 2, K equal to 1. Now, for each the beta G and T are D-symbol curves generated by a backward radial SLE kappa minus 6 process, starting from Zj, Zk. Second, if Tk is a finite stopping time for beta Kt, and if Tg, capital Tg of Tk is the first T, so that the support of beta G and T intersects the support of beta Ktk, then the transformation of the family beta G and T up to capital Tg of Tk via the map Fktk is a backward radial SLE kappa minus 6 process starting from Fktk of Zj and B beta Ktk, where Fktk equal to F associated with beta Ktk. Here, the S beta is the support of beta, which is an arc on the T. B beta is the base of beta, which is a point on the unit circle. And F beta maps the T without the support onto the T without the base. Now I explain. Okay, now if I let phi j be the welding induced by beta gt, assume that the above theorem holds, and the two backward SLE kappa, backward radial SLE kappa minus 6 processes are coupled according to the theorem. Then we will show that phi 1 equal to phi 2, which then implies the main theorem. Okay, now let Tk be fixed. The transformation of beta gt up to the time, stopping time, Tg of Tk is the heating time. Via Fktk is a backward radial SLE kappa minus 6 process, starting from the Fktk of Zj, B beta Ktk, which induces a welding. This welding is an involution of, this welding is an involution of the whole unit circle with two fixed points. The B beta Ktk is one fixed point, so we can also view it as an involution of T without B beta Ktk. Now, since Fktk maps the unit disk without support of beta Ktk onto the unit disk without the base of beta Ktk, so the beta gt up to Tg of Tk itself induces a welding, which is an involution of the unit disk without the support of beta Ktk. Thus, we conclude that the union of the support of beta gt up to that stopping time is equal to the complement of the beta Ktk in the unit circle. This shows that the support of beta j at time Tg of Tk and the support of beta Ktk, they share two endpoints. Since both beta j, phi j and phi k flip these two endpoints, so they agree on these 2 points. Letting Tk vary, we conclude that the two weldings are the same. Here is the picture. The blue arc is mapped to beta Ktk, is a blue curve. The two endpoints of support is mapped to the base of beta Ktk. Okay. And these 2 arcs share 2 endpoints. Okay, it remains to prove the theorem about coupling 2 backward radial SLE kappa minus 6 processes. To construct the coupling, we use the idea in the proof of the reversibility of forward called SLE kappa for kappa less than or equal to 4. First, we construct local couplings. Let I1, I2 be 2 closed arcs on the unit circle so that they are disjoint, and the interior of Ij contains Zj. Let beta gt be a backward radial SLE kappa minus 6 process, starting from Zj, Z3 minus J. And let Tg of Ij be the first time that the support of beta gt is not contained in the interior of Ij. So it's the first time it touches the endpoint of Ij. We say that the 2 processes are well coupled within I1, I2 if the following holds. If Tk is a stopping time for beta kt, which is less than or equal to tk of ik. Then the transformation of beta gt up to tk of ij via fktk is a stopped backward radial SLE kappa minus 6 process start from fktk of zj, the base of beta ktk. Such coupling can be constructed by weighting an independent coupling of two backward radial SLE kappa minus 6 processes by a suitable Ladon-Nicodim derivative. Here we use a standard argument on Lorentz equation by Lauder, Sherman, and Werner. Then we use a stochastic coupling technique to lift these local couplings to global coupling and finish the construction. So this ends the third section. Then we talk about tip of forward.
How much work is in that last sentence?
Pardon me?
How much work is in that last sentence?
Because we almost repeat what we already did. Just quote the theorem, then finish it. It's, the work is already done in previous work on the forward SLE. Okay, tip of forward SLE. Now, we now show an application of the symmetry result of backward called SLE welding on the study of forward SLE curve. We will use the forward backward SLE symmetry. We say that for kappa less than or equal to 4, let beta t be the H-symbol curve generated by a backward called SLE kappa process. Let gamma be a forward SLE kappa trace. Then for every t, the beta t minus square kappa bt, that's the driving function, has the same law as gamma up to t. But the family does not have the same law. Only true for every fixed deterministic time t. First, let's restate the theorem about the conformal equivalence between backward called SLE kappa and the backward radial SLE kappa minus 6. We now, I'll state the theorem again. We now focus on the conformal maps. And for the purpose here, we assume that backward radial SLE process generates a family of D star symbol curves. The D star is the exterior of the unit disk. Here is a theorem. Suppose W is a mobile transformation from the upper half plane onto the D star. Then there exists a coupling of backward called SLE kappa maps Ft with backward radial SLE kappa minus 6 maps Ft star. Starting from W0, W infinity, a time change function U, and a family of mobile transformations Wt from H onto D star, so that Wt compose Ft equal to F star Ut compose W for every t. Here's a picture. The top two pictures are backward called SLE. The bottom two pictures are backward radial SLE kappa minus 6 processes. And Ft, so this commute, and Wt and W are mobile transformations from the upper half plane onto the exterior of the unit disk. And the Wt maps that curve to that curve. Okay. Although the family of backward radial SLE kappa 0, okay, let 0 value be any number less than or equal to negative kappa over 2 minus 2 curve, those beta t star is not increasing. We may define a single curve beta star from this process. The way we do it is first we define a map ft pound equal to e to the negative t times ft star. Then ft pound is a conformal map defined on d star and fixes infinity. The factor e to the negative t is chosen so that the derivative at infinity equal to 1. As t goes to infinity, the maps ft pound tends to a conformal map f infinity pound defined on the exterior disk, and the infinity map is fixed and the derivative at the infinity is 1. Then the image of the exterior disk under F infinity pound is equal to the complement of beta star in the Riemann sphere. The beta star is a simple curve, starts from 0 and ends at some point Z0. We call beta star a normalized backward radial SLE kappa 0 curve. Moreover, for every positive t, there is a conformal map ut defined on d star, so that F infinity pound equal to ut compose ft star. The ut of d star equals to c Riemann sphere minus a segment of beta star near 0, and ut of beta t star is a segment of beta star near its end other than 0. Here is the picture. The ft star f infinity pound and ut are conformal maps defined on the exterior of the disk, and they all preserve colors. So the ut maps the red curve to this red part, and it maps the boundary of unit circle to this blue curve. Okay, that's a picture. Using the time reversal symmetry of the stationary radial Bezier process, we obtain the following theorem. That's if beta is less than or equal to negative kappa over 2 minus 2, then a normalized stationary backward radial SLE kappa 0 curve has a law of a whole plane SLE kappa minus 4 minus 0 curve stop at time 0. Here, 0 less than or equal to negative kappa minus kappa over 2 minus 2 implies that minus 4 minus 0 is greater than or equal to kappa over 2 minus 2. And recall that a whole plane SLE kappa 0 prime curve with kappa less than or equal to 4 and 0 prime greater than or equal to kappa over 2 minus 2 is a simple curve from 0 to infinity. And the time parameter is from negative infinity to infinity. So the time 0 is some time in the middle. In particular, a normalized stationary backward radial SLE kappa minus 6 curve is a stopped whole plane SLE kappa plus 2 curve. We will apply the conformal removability of SLE kappa curves for kappa strictly less than 4, which follows from work by Peter Jones and Stan Smirnov and Stefan and Odette. Now we're combining the symmetry of the backward radial SLE kappa minus 6 welding. Construction of a normalized backward radial SLE kappa minus 6 curve and its whole plane SLE kappa plus 2 description, and the conformal removability of SLE kappa for kappa less than 4, we get the following theorem. It says that for kappa less than 4, let beta be a whole plane SLE kappa plus 2 curve stopped at the 0 with 2 ends 0 and Z0. Then the reversal of Z0 minus beta has the same distribution as a time change of beta. I want to remark that this theorem is about a stopped whole plane SLE kappa plus 2 curve. It's different from the reversibility result by Miller and Sheffield. We say that for kappa less than 8 and 0 in a certain interval, the reversal of a complete whole plane SLE kappa 0 from 0 to infinity has the same distribution as a time change of a whole plane SLE kappa 0 curve from infinity to 0. Our theorem does not hold if kappa plus 2 is replaced by any other 0. We now show that if gamma is a caudal SLE kappa curve, then for any positive t, the gamma image from 0 to t, gamma curve from 0 to t can be mapped conformally to an end segment of the normalized curve beta star, so that tip gamma t is mapped to the open end of beta star. That's the end other than 0. The proof, as we call the proof of conformal invariance between backward caudal SLE kappa and backward radial SLE kappa minus 6 gives a family of mobile transformations Wt from the upper half plane onto the exterior of the unit disk, and a time change function u, so that Wt maps beta t onto beta star at u of t. Also recall the construction of beta star from the normalized curve beta star from the family beta star t gives a family of conformal maps UT defined on the exterior of U disk, so that UT of beta star T is a part of beta star near its open end. So now we let Vt equal to U sub U of T compose Wt. The Vt is a conformal map defined on the upper half plane, so that the image of beta T on the Vt is an end segment of beta star, and the tip of beta T is mapped to the open end of beta star. Now, using the forward-backward SLE symmetry, we see that this result holds with beta T replaced by the gamma up to time T after a translation. So recall that picture, Wt maps this curve to that curve on the circle. And also recall the U sub Ut maps that circle to this red circle. So combining these two maps, then we have a map on the upper half plane that maps that curve to this red curve on the bottom picture. Recall that beta star is a stopped whole plane SLE kappa plus 2 curve. So gamma from 0 to 1 can be mapped conformally to a tip of a stopped whole plane SLE kappa plus 2 curve. Since beta star satisfies reversibility, we can now conclude that gamma from 0 to 1 can be mapped conformally to an initial segment of a whole plane SLE kappa plus 2 curve, so that the gamma of 1 is mapped to 0 instead of the open end. Thus, if the initial segment of a whole plane SLE kappa plus 2 curve satisfies some property that is preserved by conformal maps, then the tip of gamma from 0 to 1 also satisfies such property. As an example, we get the ergodicity of SLE kappa near its tip. We have following theorem. Let kappa be strictly less than 4, gamma be a chordal SLE kappa curve, and suppose for t less than 1, we let V of t be the capacity of the curve from t to 1. So we forget about the curve from 0 to t. And let h of t be the harmonic measure of the left side of gamma from t to 1 in the complement of gamma t from t to 1 viewed from infinity. Then for any continuous function f, almost surely the following formula holds. Here V of t is decreasing with V when t goes to 1, the V of t tends to negative infinity. The function sine of x over 2 to the power 8 over kappa plus 2 is proportional to the stationary density of the radial best cell process xt for a backward radial SLE kappa minus 6 or a forward radial SLE kappa plus 2. That's all. Thank you. And happy birthday, Greg.
Thank you very much. Dapeng, are there any questions?
Oh, yes. Yeah, I mean, I see that it's a subtle thing because one always tries to think that there is more reversibility in the coupling with Gaussian free field that there might be, but is there a way to interpret this in terms of loops? I mean, by discovering some sort of the welding along a loop, doing part of the loop, and then try to see that there is some growth on both sides rather than the full plane or radial.
I did not think of that in that way.
Oh, okay, so
I don't know.
got you.
Yes, thank you. Yes.
So the statement that you said if you draw a whole plane SLE kappa plus 2 to a stopping time,
Yes.
then you get a curve to a time, and that's reversible.
Up to capacity time 1.
Draw to a capacity time,
Yes.
and then when you look at that set, you can't tell which point was the start and which was the end.
Yes.
What's that?
Yeah, I was sort of thinking whether you cannot view this as part of some loop, right?
Well, so I was going to say, have you thought about kind of What would be the quantum version of that statement? That if you run until a notion of kind of quantum length instead of capacity, then you should get. We thought, what's the right statement there?
I guess quantum length corresponds to different SLE kappa zero process.
Yeah, I mean, I wonder if you can get an analog of this statement for a range of rho values.
I guess different
Defining the stopping time
rho values
differently.
correspond to different measure on the curve. If you sample a point on the curve according to other measures, you should view different SLE kappa zero process. I don't know whether this answers your question. It's my guess.
Why would the time that you're sampling on affect the role of a kappa rho process?
Well, for instance, if you pick it according to natural time, it has to be two-sided radial because essentially,
Yes.
I mean, it follows from the fact that if you integrate them all up, you just get.
Okay.
So that's just one example of an SLE kappa
Right,
rho
it's
process that you would get. I assume natural time is an example of quantum time, or at least different.
So is that obvious that if you're doing natural time and you're doing this two-sided radial,
Yes. That's SLE kappa
then maybe it's obvious. Is it obvious?
I think you can do it as a bit of an extension of some result, but it doesn't mean that there's not a very easy way to do it.
Because if you just take a long SLE curve, you pick one point, and then you pick a point 1 unit later, you sort of zoom in there, you can't tell the two sides apart.
If you start with SL kappa 2, whole plane SL kappa 2, and you stop at a fixed natural parameterization time, then maybe you cannot differentiate the starting point and the point.
Right.
SL kappa 2 corresponds to two-sided radial.
Okay. Yeah.
That's the same rho value which you get from the quantum one. You take two gamma quantum wedges and you just shift time.
So this is just capacity parameterization.
Yeah, well, I think we'll thank Dapeng again for very thought-provoking talk.